ये क्लियर करना है। It's not a compulsory course. हम जीतते हैं।
अस्सलाम वालेकुम मैम।
वालेकुम सलाम तहरीन, क्या हाल है?
मैम आई एम गुड, आप कैसी हैं?
मैं बिल्कुल ठीक हूँ। सो हैप्पी न्यू ईयर।
हैप्पी न्यू ईयर टू यू मैम।
Happy New Year, ma'am.
हेलो बेटा, हाउ आर यू?
I'm fine, ma'am. What about you?
आई एम फाइन, थैंक यू। तो क्या किया आप लोगों ने छुट्टियों में?
मैम लैब
Ma'am,
रिपोर्ट्स एंड असाइनमेंट्स।
क्या?
यस मैम।
नहीं, यू शुड गेट टाइम, यू शुड टेक द टाइम टू रिलैक्स ऑल्सो। ठीक है, काम भी करें लेकिन डू गेट सम टाइम टू रिलैक्स, ठीक है ना?
यस मैम।
व्हाट अबाउट यू असद?
ma'am, I read some really good books. I read about the Caesar Civil War in ancient Rome.
वाओ,
I read about the Punic Wars between Rome and Carthage. And I read about the end of Byzantium, the Eastern Roman Empire. And I also read about particle physics.
wow, that's interesting. So you do have an interest in the Romans, the Roman
I
Empire.
actually have an interest in history.
You have an interest in history. So what parts of history are you more interested about?
I actually study war-oriented history. Like by now, I have studied the medieval era, and now I was going towards the Bronze Age, medieval era of Europe, Asia, Middle East, Africa, and South Asia.
Okay, so what part of our history are you interested in?
Ma'am, if you were to ask me about the most interesting historical events, I would at first point out the invasion of Genghis Khan from Mongolia to almost the entire world. And the second was the rise of the Rashidun Caliphate. And the third
The rise
was
of
the
what? The rise of what?
Rashidun Caliphate.
Okay, so we are talking about which era is this?
Rashidun Caliphate started in 632 BCE.
Mm-hmm.
Yeah, and it had 4 caliphs.
In
And
BC.
by
No,
the
wait a minute. In BC.
yes, ma'am.
Are you sure this is BC?
Yes, ma'am. I can't hear you. Please, can you
Are
please
you
repeat what you
sure
just?
this is BC?
Ma'am, 632 AD, Anno Domini.
Yeah. Okay. So I thought
I
you said
accidentally.
BC. Okay. Okay, good. So it would be interesting if we can sometimes maybe talk about maybe Mohenjo-daro or the Indus civilization or something like that, right?
Yes, ma'am. It in fact is.
Yeah. Okay. So hello, Eman. Hello, Ramin.
Hello.
How are you?
Hello, ma'am.
ये कौन बोल रहा है? Ramin. Okay, Ramin, how are you?
I'm fine, ma'am. How are you?
I'm fine, thank you. Happy New Year.
Thank you, ma'am. Same to you.
How were your holidays?
Ma'am, quite boring.
Quite bored. Oh, you like studying. That's great. Okay. Right. Hello, Shaggy.
Hi, ma'am. How are you?
I'm fine. How was your holiday?
It was boring, I guess, because
Boring, really?
after a few days, I thought maybe the class should have started. Yes, ma'am, because we have nothing to do at all.
Uh-huh. Okay. So I hope. What about Eamon? Hello, Eamon.
Hello, ma'am.
How are you?
I'm fine, ma'am. How are you?
I'm fine, thank you. How were your holidays?
Okay.
Okay,
Little boring.
little boring. So three people are bored, right?
Yes.
Okay, but I hope that all of you are refreshed. At least you got time to relax and all that. Okay,
Yes.
good, great.
And how
So
were your holidays?
my holiday was okay. I did relax. I did start waking up a little bit later than usual, which I was surprised. I normally don't wake up late. But yeah, okay, I got time for doing some stuff that I wanted to do. And I also got some time for myself. It was fine on the whole. So, are you ready to study?
Yes, ma'am.
Yeah? Okay, so let's start. So, everyone is present, I think. Is someone missing from the class?
Ma'am Durdana.
Durdana, where is she? She's a hostelite. I don't know if she managed to come to the hostel yet. Asad, you're not in the hostel, right?
No, ma'am, I'm in my hometown right now.
So, you're in your hometown during the lockdown.
Yes, ma'am, I'm in my hometown.
Right. Okay, so Durdana, you I think stays in the hostel. What about you, Ramin?
Ma'am, I'm at home.
You're also at home. You didn't come to the hostel, right?
Yes, ma'am.
Okay, right. Okay, great. Okay, so only one person missing. That's okay. Let's share. Okay. So what were we talking about the other day? What are
Beta
we
decay.
studying?
Ma'am, beta particles.
Beta decay.
Beta decay.
Yeah, great. Okay. Who can do a small recap for us? Yeah, let's do a small recap. So what
During a
happened?
beta, the electron
Wait.
turns.
Sorry. Okay, start again. Yes.
During a beta decay, a neutron turns into a proton and it ejects an electron out of the nuclei.
Mm-hmm. Okay. Anyone else? Would anyone
Ma'am,
like
there
to?
are three types of beta decay.
Who is this?
That's negative.
Wait,
Ramin.
Ramin. Yes.
Ma'am, there are three types of beta decay. That's negative beta decay, positive, and orbital. And we also studied.
Okay, that's okay.
Can you
That's
hear
enough.
me? Hello.
Let's go to a new person now. Yes, Iman, would you like to tell us what is negative beta decay? Or Tahim? Or Shurjeel?
Ma'am, it's in which electron is emitted along with the antineutrino. A neutron is converted into proton, and electron
Okay.
and antineutrino are emitted.
Okay, great. Okay, so um, let's start from here. So we have three types of beta decay. We have the first one, which is negative beta decay. It's represented like this. And in this case, we can write the reaction where a neutron is changing into a proton with the emission of an electron. The second one is the beta positive decay. In this case, a proton is changing into a neutron plus a, what is this? Eamon, what is this symbol? Wait, Eamon,
Positron.
जिससे पूछा उसको बताने दो ना. I was giving her a chance to answer. ठीक है? Okay, so and the third one is a proton plus an electron. It gives you a neutron, and this is known as the orbital
Orbital electron.
orbital electron capture, right? You can see that, and the representation for this is like this. So this is one type, this is second type, and this is third type. Also, you will notice that the electron in the third type is on the left hand side of the reaction, which means this electron is being captured. Okay.
Excuse me, ma'am.
Yes.
Ma'am, in order to conserve the momentum, should there be a neutrino
Of
produced in
course.
this?
Sir, were you in the last class?
Yes, ma'am.
Before the last class we had? Yes, of course there are neutrinos. I'm just coming to that. I've also talked about this in the last class as well. So we initially started with this, but then you know that as people worked further on this, they found that there was something missing, and ultimately it was found that this particle was a neutrino, right? So for example, in this case, we have this particle here. What is this? This is the
This is an
Antineutrino.
anti-neutrino.
this is a
Neutrino.
anti-neutrino.
Anti-neutrino.
Neutrino.
Antineutrino.
Anti-neutrino.
Anti-neutrino.
Okay. And then also in the second case, we have a particle which is, this is called
Neutrino.
neutrino, right? And then in the third case, we again have a neutrino. So these were the three types of decay. Initially, you know, like the initial step, I was just proceeding from there, was that these particles were not known at that time. So they just thought that the neutron is converting into proton with the emission of an electron. So this was what they knew till that. But later on, what they observed was that when they did the calculations and all that, and there seemed to be something missing, because the two sides were not really the energetics were not being balanced properly, and then that opened a new question that there might be the existence of a new particle, and then they found this neutrino, right? Okay. So I'm going to clear the board now. Okay.
Okay, ma'am.
Uh, right. Another thing we talked about was the fact that when we do the energetics, we talked about the concepts of the Q value, right? So what is the Q value? Let's give a chance to someone to reply who has not replied before. Who would like to do this? The Q value is
Ma'am, the amount of energy that is produced in a nuclear reaction, and it is usually in mega electron volts.
good. Who is this speaking?
Ma'am, me, Tehreem.
तहरीन बेटा नाम बताया करो ना क्योंकि I cannot see you. ठीक है?
Okay, ma'am.
ठीक. Okay, so we utilize the concept of the Q energy, right, to work with this. And based on the Q value, we were able to write the equations for this. You remember them, you know? We've calculated we also used the concept of the energy being a product of mass and velocity of light. We also talked about TP, TE, and T nu. Somebody tell me who has not answered before what TP, TE, and T nu bar stands for. You can?
Should I?
Nay, let's invite someone to volunteer who has not answered before. Would anyone like to try?
Ma'am, TP, I guess, was proton coil or recoil?
ये कौन बोल रहे हैं?
TP. Ma'am, Tehreem.
Tehreem. Okay. What is T? T is the symbol T is being used for
Energy.
Kinetic energy.
Kinetic energy.
Right. So T with a subscript P means this is the kinetic energy of the proton. T with the subscript E is this is the kinetic energy of the electron. And T with the subscript of U is the kinetic energy for the neutrino or the antineutrino. Right? Okay. And then we did the derivations for this and the explanations for this, which you already have in the last class. And about the neutrino, when we talk about the neutrino, some of the properties of the neutrino are that it is massless, right? It is considered to be massless, and therefore it is considered to move with the speed of light. Okay. What other property are we familiar with? Did we mention maybe in the last class?
Neutrinos properties, it rarely interacts with other matter particles.
Okay.
And since it is chargeless and massless and is not associated with any active field that we see in our everyday lives, it becomes almost impossible for us to detect a neutrino. That is why we call them ghost particles.
Great. Yes. It becomes very difficult to detect them because we cannot, because of their properties like being chargeless and so on. Okay. Great. Okay. And did we talk about any other property? Can someone name any other property we mentioned? We might have mentioned. No, I think this is what we did last time. So let's go further from here. Okay.
Okay, ma'am.
All right. So um okay. So what kind of decay were we working with last time?
Electron capture.
Are you sure?
No, ma'am, I think so. Positron.
Yes,
मैम
ma'am, I'm sure.
ऑर्बिटॉल वाला
नहीं.
पढ़ना था अभी हमने.
Yes,
वही ना
ma'am.
इलेक्ट्रॉन कैप्चर ही कहते हैं उसे, ऑर्बिटल इलेक्ट्रॉन कैप्चर.
वो पढ़ना था ना?
यस मैम.
यस मैम.
जो पढ़ा था वो कौन सा था?
मैम पॉजिटिव एंड
मैम
नेगेटिव
नेगेटिव बीटा
पढ़ा
डिके
था.
एंड पॉजिटिव बीटा डिके.
कौन सा?
नेगेटिव बीटा डिके एंड पॉजिटिव वाला.
नेगेटिव वाला पढ़ा था।
एंड पॉजिटिव
Positive?
दोनों पढ़ लिए थे.
नहीं, I don't think so.
Yes ma'am, because we discussed the q values of both of them.
यस मैम.
कौन सी इक्वेशन थी लास्ट that you did?
मैम दैट वाज
Cube
9.9, ma'am.
क्यू बी पॉजिटिव
9.9 की थी?
इज इक्वल टू.
Yes, ma'am.
यस मैम 9.9.
ठीक है, fine. Okay, so you're right. We did beta negative and beta positive. ठीक है, so now we are talking for electron capture. Okay, so for an electron capture process, okay, we can write the equation where we have a nucleus, right? And when it captures an electron, we should have another nucleus, in which case this can be represented by x prime, and the atomic number decreases by 1, and the neutron number increases by 1 and plus a neutrino. Okay. Now this x prime is in an atomic excited state. In this case, x prime is in an atomic excited state. Immediately after the capture. So it's not in a stable state, rather it's in an excited state. So this means that if the capture takes place from an inner shell, okay, so if the capture takes place from an inner shell, the K shell, for instance, okay, you're familiar with the K shell, right?
Yes, ma'am.
Yes,
तो
ma'am.
समझ आ रही है ना? The shells जो होते हैं हमारे K, L, M, N, है ना?
Yes,
So
yes, ma'am.
if we talk about the innermost, let
Yes,
us take an
ma'am.
example.
KLMN. Yes, ma'am.
हाँ, ठीक है. So if we take, let's say, the innermost shell, which is the K shell, then we can say an electronic vacancy in that shell Okay, is this sentence clear? If the capture takes place, if the capture of what? Capture of the electron takes place from an inner shell, the K shell, for instance, an electronic vacancy in that shell results. ये तो concept आपको clear है ना कि जब एक shell अपना when one
Yes,
shell
ma'am.
loses an electron, a vacancy क्या होती है? It's a deficiency of the electron, right? So a vacancy in that shell results. ठीक है? And what happens when there is a vacancy in a atom? What are
मैम
the
वो रिएक्शन मतलब इलेक्ट्रॉन्स वगैरह वो जो है
Okay, let's
We
try.
can see in general wording, I would say the tendency to get something which it has lost.
So what's the possible way of doing this? A possible way would be that
Ma'am, it
this
tries to become stable
vacancy,
by absorbing an electron.
acha, this vacancy is quickly filled.
From the upper electrons.
Yeah, that's highly probable.
From the outer shell.
Yes, very good. So filled as electrons. कौन बोला था अभी?
Asad.
ये कौन लिख रहा है मेरे इसके ऊपर? Somebody did something. Let's see. कौन है इसमें? Okay. Okay. As electrons from higher shells make downward transitions. So there's always a possibility that a electron from a higher shell will jump into the vacancy into the lower or inner shell. And when this happens, it's also possible that there will be some extra energy in that electron, which it may emit, okay? So, and it may emit this extra energy as a characteristic X-ray. Okay, let's try to understand this sentence again. The vacancy is quickly filled as electrons from higher shells make downward transitions and emit characteristic X-rays. So just as we said, whenever whenever an atom is in an excited state, the most probable thing that will happen will be that the atom will try to attain stability, right? And in order to be stable, it's probable that a higher level electron jumps into the lower level vacancy. When an electron jumps from the higher state to the lower state, it normally gives off some extra energy that it may have. You know, every energy level corresponds to a definite amount of energy. This is the concept we get from quantum mechanics, right? that energy is always quantized. Okay, so there's a quantization concept of energies, and there are diagrams and graphs that illustrate this: the energy in the lower level and then the energy in the upper level. These are definite amounts of energy. So this difference in energy of the electron coming from the higher shell to the lower shell will be emitted off, just like we have been making many calculations and derivations that show how the energy has to be calculated or balanced, or energy plays an important part in all of this. So one of the ways that this energy is emitted is by emitting characteristic X-rays. So what are X-rays?
X-rays are high energy photons that are usually transmitted by the inner transition of electrons in a large atom.
Okay, great. So X-rays are basically photons. We all know what photons mean, right? Photon is basically defined as a quantum of energy, right? And photon is also a particle. It's defined as a particle. Photon, we also know, is a electromagnetic radiation. So X-rays are a kind of electromagnetic energy, radiation. These are high energy radiations. And characteristic means that you know, these radiations emitted from the K shell would be called the K characteristic radiations. And if they're emitted from the L shell, they will be called the L shell characteristic. So they're defined according to these different transitions that take place. So there, that's where the term characteristic comes from. Okay. Now, whether, and again here also you can also relate this to the again very important concept we have in quantum physics, which is the wave particle dualism. You know that these are all particles and they also behave as waves, including the photon, including the electrons, including X-rays. Okay, so whether one X-ray is emitted or several, the total X-ray energy is equal to the binding energy of the captured electron. So here we've also utilized the concept of binding energy. Again, this is again an important concept of we've been doing it again in the calculations that we've been doing for the energies and the different kinds of decays. Okay. So now I'm going to erase the board.
Okay, ma'am.
Okay. Thus we can say the atomic mass of X prime immediately after the decay is greater than the mass of X prime in its atomic ground state by B Bn. Okay, so what is Bn?
Ma'am, binding energy.
Very good.
Binding energy, man.
Binding it. Very good. So in this book, for example, capital B is used for binding energy. Just like I said before, some books are using the symbol Be and some books are using the symbol just B. And what is N?
It denotes nuclear binding energy.
No. Okay, here
Ma'am, it's number.
it's a number, right? Okay, and this number in this case represents the number of the shell. Okay, so n in this case can correspond to k or l or m and so on. Okay, and then we can say the q value then given by by a similar process as we did for the previous two types of decays, we can also do it for the electron capture, and we can write this equation. Multiplied by c squared n minus b n. So this is equation 9.10. I would also like to make an announcement that if this meeting ends, which it will in a few minutes, you can again click the same link to join again. Is that clear? And
Okay, ma'am.
great. Okay.
Okay, ma'am.
So now in all of these expressions that we've been doing, including the previous class as well, we can refer to the decays between nuclear ground states. Um, so all of the, we're talking about decays between nuclear ground states, and if the nuclear state X prime is an excited state, then the Q value must be accordingly decreased by the excitation energy of that state. So we can write this as so. Okay, then we can say the Q value must be accordingly decreased by the excitation energy of the state. So the Q value must be accordingly decreased by the excitation energy of the state. So therefore, we can say that Q excitation is equal to Q ground minus the excitation energy. So this is equation 9.11. So you remember what the excitation energy is? The excitation energy, I think we defined it before as well. So this is the energy required to change an atom or a molecule from one quantum state to another of higher energy. So it is equal to the difference in energy of the states and is usually the difference in energy between the ground state of the atom and a specified excited state. So this is another way of saying it. So it is equal to the difference in energy of the states and is usually the difference in energy between the ground state of the atom and a specified excited state. Like for example, we talked about the transition from an outer shell to an inner shell, then this will be equal to the difference in energy of the states and is usually the difference in energy between the ground state of the atom and a specified excited state, right? Okay. Acha, I think I will end the meeting and start a new meeting, okay? Is that clear?
Okay, ma'am.
Yes, ma'am.